Okay, so we are going to start, as I said, frequency selective circuits, or we are going to discuss how the frequency is going to affect the response of your basic RLC circuits, RL circuit, RC circuits. In general, we call those circuits filters. Frequency selectivity is the basic characteristic of pretty much any electronic or electric circuits. You pick up any electronic circuit, you have diodes, you have transistors, BJTs, MOSFETs, thyristors. All those devices, they have internal capacitance. So anytime you are putting any electric circuit and you are varying the incoming frequency, then your response at the output is different based on the frequency. Why? Because your capacitor is dependent on frequency, the reactance of the capacitor, 1 over j omega c, and the reactance of an inductor is also dependent on the frequency j omega l. So if omega is changing, then the reactance of those components are changing, and your response is going to change at the output, whether that response is current, voltage, power dissipated, or whatever is that. So that's what we are going to look at. Very simple, very basic. As chapter number 16, but initially the part that I'm going to discuss is not in chapter 16 of the book, which is the first order high pass and low pass filters. The second order filters or second order circuits are in the book, which are RLC circuits. So we are going to start with, let's see, and frequency. So if a circuit has inductors or capacitors, and or rather, and or capacitors, their reactance change as you change the frequency of the circuit. Frequency of the circuit means, of course, you're changing the source frequency, or the incoming signal has different frequency. If a circuit has inductors and or capacitor, their reactance change as you change the frequency of the circuit, yielding different response at different frequencies. Now, as I said, the inductor and capacitor can be external, like we are using, or they can be internal, as the capacitor of the electronic components. Between base and collector, there's a capacitance, base and emitter, collector and emitter, and so on and so forth in a BJT. And in diode, of course, at the junction, you have a junction capacitance as well. So these circuits are called in general, these circuits are called filters. What are filters? The filters are the circuit that give different response at different frequencies. Now, that doesn't mean that every circuit is a filter that is giving different response at different frequencies. Your amplifier, if you're using an operational amplifier and creating an active filter or creating an amplifier, the intention of that amplifier is not to act as a filter, but it is going to act as a filter at different frequencies. That is, in a range of frequencies, it is going to amplify the signal as you want it to amplify. Let's say you set the gain of the amplifier to be 10. Your input signal is coming at 1 volt, output signal should be 10 volt, but it's going to be 10 volt only over a band of frequencies. If you go outside that band, then your gain is going to reduce because your circuit is only going to behave as the proper amplifier over the range of frequencies. Outside the range, it is going to reduce the gain, or it's going to basically act as a filter, and it is not going to give you 10 volt for a 1 volt coming in. So the intention of that circuit is not to act as an amplifier, but as an engineer, as a designer, it's your job to operate that circuit or design that circuit for the range of frequencies at which your system is operating. Because if you go outside the range, it's possible that that amplifier starts acting as a filter and reduce the gain, and it's not going to be the same gain as you design the filter, design the amplifier for. So every electronic circuit, it intentionally or unintentionally act as a filter, basically. Some are designed to be filters, some are not designed to be filters, but they work only over a range of frequencies, and outside that range of frequencies, they're not going to give you the intended gain as you are looking for. So we're going to start with looking at the basic, what we call first order passive filters. So we're going to start looking at the very basic first order passive filters. First order means that you have only one reactive component. So when you write the equation in time domain, it is going to be first order differential equation, as we did for RC circuit and RL circuit in chapter number 7. Passive means that they only have the passive component, resistors, inductors, and capacitors. And in what we call the pass band, over which these circuits are working, your output cannot exceed the input value. It will be either equal to the input value or it's going to be less than the input value. And those filters are called passive filters. Now, on the other hand, you can have active filters. Active filters, they are made out of electronic components, operational amplifier, inside operational amplifier, of course, you have transistors and diodes and whatnot. But active filters are different from the passive filters such that they provide two functionalities. They provide filtering of the signal. So over frequencies, they let the signal go. Other frequencies, they stop the signal. In addition to that, they also provide amplification of the input signal over the range of frequencies that they let the signal go. So the output can be larger than the input for active filters over the pass band. Whereas for passive filters, output can never be larger than the input signal over the pass band. And the bands where they're stopping the signal, of course, the output is going to be less than the input signal anyways. So that's why they are called passive filters. And in integrated circuits class, we discuss active filters, which is you may be taking, well, not, it's not offered next semester, but it's going to be offered next spring. So you'll be taking that class next spring. Some of you don't need it, of course, your computer concentration, but electrical concentration will be taking that class. Yeah. This course, there's only passive filter because we are not discussing operational amplifier in this course, right? Okay. So in general, you have passive filters, you have low pass, first order passive filters. Now the low pass filter, basically the response of low pass filter look like this. Now I'm going to draw both the ideal response and the practical response. So the ideal response of the low pass filter look like this. Let's say V out, and this is ideal. Your x-axis in this case is either f, your frequency, or omega, whichever you're taking, either in hertz or radian per second. And this is your output. And as you can see, the output is equal to the input signal up to a frequency, what we call the cutoff frequency, FC. Let me use, actually, let me just use this. FC is the cutoff frequency, which we also call, let me see, let me write this down here. So FC is equal to cutoff frequency. It is also called corner frequency. It is also called 3 dB frequency. So all the names are for the same frequency. And in general, the concept of cutoff frequency is the frequency up to which your filter is going to let the input signal go to the output. That's the cutoff frequency. Now, mathematically, we're going to see what is the definition of cutoff frequency. But for ideal filter, as you can see, output is equal to the input signal up to the cutoff frequency, and after the cutoff frequency, the output becomes 0. So all the input signal is passing through the circuit up to the cutoff frequency, ideally, and after the cutoff frequency, it goes down to 0. So for the ideal, ideal filter, cutoff frequency is the frequency up to which the signal is going to pass, and after which, for the low pass filter, after the frequency, the signal is going to stop. As far as practical first order filter is concerned, you cannot have this sharp of a drop at the cutoff frequency. It's just not possible, because again, circuits, capacitors, inductor, they charge and recharge or discharge, and it takes them some time to charge and discharge, so they cannot instantaneously discharge at cutoff frequency and the response goes down to 0. So the ideal filter response looks like this. Ideal low pass filter response, something like that. So they start at input. Now, of course, the first frequency we are assuming, let's say it is 0. What does 0 frequency mean? In general, what does 0 frequency mean? That the circuit is operating at DC, right? There is no frequency. Circuit is operating at DC. So at DC, remember, if you have a capacitor in the circuit, capacitor is going to be fully charged open circuit, steady state. If your inductor in the circuit, fully charged short circuit at a steady state. So at DC, for the ideal filter, at DC, your output and input are equal for ideal low pass filter. But as you start increasing the frequency on the x-axis, as you can see, we are increasing the frequency. As you start increasing the frequency, the output starts going down. At the cutoff frequency, the output becomes 1 over square root of 2 times the peak value of the output, which in this case is the input voltage, or 70.7% of the input voltage. This is what happens at the cutoff frequency, and this is actually the definition of cutoff frequency. Definition of cutoff frequency is the frequency at which the output of the circuit drops down to 70.7% of its peak value, which in this case is the input voltage, is the cutoff frequency. So remember this definition, because you are going to be asked about what is the cutoff frequency, and anytime somebody asks you what is the cutoff frequency, that's going to be your answer, that the frequency at which, for any filter, the frequency at which the output goes down to 70.7% of its peak value is called the cutoff frequency. So this is the response, ideal and practical response of a first order, a low pass filter, whether it's a first order, second order. As you start increasing the order of the filter, let's say you have a second order low pass filter or third order low pass filter or fourth order low pass filter, what changes is that the response start becoming closer and closer to the ideal response. That's what changes. So right now you will have, it's going down like that. But as you start increasing that, circuit is going to become, it's going to become more complex. But the response start kind of aligning with your ideal filter response, close to ideal filter response. Yes. Yeah. Hmm?
Isn't that also RMS value? The formulation for RMS to peak?
So again, RMS value, you always assume that RMS value is for sinusoidal signal. Well, RMS value for sinusoidal signal is 1 over square root of 2, that is correct. But RMS value is not 1 over square root of 2 for any signal, right? So this has really nothing to do with RMS value. I'm gonna show you the derivation as why at cutoff frequency the response is 0.707. It has nothing to do with the RMS value. It's just a coincidence that RMS value is also 1 over square root of 2 times the peak value of a sinusoidal signal. All right, so first order low pass filter, there can be first order low pass capacitive filter or inductive filter. So let's look at the first order low pass capacitive filter first. And this is very commonly used filter because it's very simple and it works decently well. And pretty much everyone is familiar with this simple circuit that we also discussed from a different perspective in chapter number 7, which is a simple RC circuit. Yeah. Say it again. If I go back, what are you asking? Yeah, that is the voltage you will observe at the cutoff frequency. The output voltage that you're going to observe at the cutoff frequency is going to be 0.707 times the peak value, and peak value in this case is the input voltage. Now, many times, or actually most of the time, when you are designing the response of a filter, you do not really plot the output versus frequency. Rather, you plot the transfer function or gain of the filter versus frequency, which means you plot the ratio between the output and the input versus frequency. In that case, basically, if you plot that, what we call transfer function, what we're going to discuss in a little bit. So if you plot the transfer function, which h of j omega, magnitude of that, which is output over input. So the ratio between the magnitude of the output divided by magnitude of the input. And this is most of the time is plotted for to display the frequency response. Curves are going to be the same. So for practical filters, the curve is going to be something like that. But in this case, the magnitude is going to be 1 because output is equal to input at DC, as we saw here. And then at the cutoff frequency, FC, it is simply going to be, your value will simply be 0.7071 because the peak value is 1. So if you plot the transfer function or the ratio between the output and input versus the frequency for any filter or for low pass filter, then curve is still going to look the same. The values are going to be scaled with respect to the peak value, which is the input value. And we'll plot the response of different filters in MATLAB, and you can do that in PSpice as well. There's one lab which you're going to be doing in PSpice, which is the bandpass filter lab. Okay, in this case, we have R and we have C. We have the input voltage, which is a function of omega, and we have the output voltage function of omega. Now, everyone can write down the equation of the output voltage in terms of RC and the input voltage. But before you even write down the equation, once you look at the circuit, can you determine what type of filter is this? Low pass, high pass, band pass? How you're going to recognize this circuit as a low pass filter? Anyone can answer that. Okay, yeah, it is because of the capacitor. So, but what quality of capacitor is going to make this filter a low pass filter? Again, remember, what thing is changing when you're changing the frequency? Reactance. So you always have to think about in terms of reactance, right? Voltage divider is how you're going to find the output. That's a different story, right? But if I give you a circuit and I say, identify if it's a low pass filter, high pass filter, whatever. To identify that circuit, you're going to start thinking about how the reactance is changing when you're changing the frequency. So tell me how the reactance of the capacitor is going to change when I change the frequency of the input, starting from 0 all the way up to infinity. At 0, what will be the capacitance? Say it again. Infinity. 1 over j omega c. Remember, 1 over j omega c. Omega is 0. It's not a number, but we say if it's close to 0, the reactance is very large. It acts as an open circuit, right? Anything that is extremely large, reactance or resistance, open circuit. So if capacitance is acting as an open circuit, and we know for DC it acts as an open circuit, right? If it is acting as an open circuit, that means you don't have any current flow. Input will be equal to output, right? Because capacitor is open, no current flow. Now, as you start increasing the frequency, what's going to happen to the reactance? It starts going down, right? And eventually it's going to become too large frequency that the capacitance is going to become what? 0. Reactance becomes 0. When reactance is going to become 0 at omega is equal to infinity, then the output is going to have 0 voltage because it will be parallel to the short circuit. In between maximum and 0, your output is decreasing, right? So it is acting as a low pass filter because at low frequencies, your output is high, and at high frequencies, your output is low. So that's why it's acting as a low pass filter. Without going into the math, you can just manipulate the reactance of the inductor or capacitor, whichever is in the circuit. And based on that reactance, you can kind of visualize it and say, when do I have high response? When do I have low response? And based on that, you can say, this is a high pass filter or low pass filter. So this is a low pass filter because reactance is very high, output will be equal to input at 0 frequency and small frequencies, and reactance will be very low at high frequencies, output will be very small as well. As far as the mathematical derivation of the output is concerned, so how are we going to find the output? Who's going to tell me? Voltage divider, and that is going to be? XC over R plus XC. All right, as I discussed with you earlier, the concept of transfer function. So the transfer function is the ratio between the input and the output. Generally represented by H, function of j omega, is output over input, which is simply XC over R plus XC. Now we're going to go ahead and plug xc is equal to 1 over j omega c. And with simplification, we can write this down as 1 over j omega c over 1 plus j omega rc, j omega c. J omega c is cancelled out. And we're going to get 1 over 1 plus j omega r c. So this is the transfer function of the low pass filter. We write this transfer function in a little different way to represent the cutoff frequency. And we write this as 1 divided by 1 plus j omega divided by 1 over rc, which is the same as this, because 1 over rc means rc is going to go in the numerator and it's going to become 1 over 1 plus j omega rc. And we write this as 1 over 1 plus j omega over omega c, where omega c represents the cutoff frequency. And why? We'll discuss that. And again, omega, remember, it's radian per second. So if the cutoff frequency is given in hertz, then you can calculate the corresponding frequencies in radian per second, 2 pi fc. Or if it is given in radian per second, then you can calculate the corresponding cutoff frequency in hertz by dividing omega c by 2 pi. So don't forget the relationship between radian per second and hertz. Omega is equal to 2 pi times f. Yeah. I'm sorry? No, it depends where the capacitor is connected in the circuit. Yeah. If you want to write this down in terms, the transfer function down in terms of cyclic frequency as a function of f, you can do that easily. 1 over 1 plus j 2 pi f over 2 pi fc, which is omega over omega c. Of course, 2 pi is cancelled out. So simply you can write down 1 over 1 plus j f over fc. So you can just replace omega over omega c by f over fc if you want to write the transfer function down in terms of cyclic frequency in hertz. All right, now we are calling omega is equal to omega c is the cutoff frequency and whatnot. How do we know it is the cutoff frequency? So for that, we are going to find, now this is a complex number, right? Whether you write this down in terms of f or you write it down in terms of omega. H of j omega is a complex quantity. Written in rectangular form because it has the real part as well as the imaginary part. So anytime you have a complex quantity, you write down in polar form to see what is the magnitude of that quantity and what is the phase associated with that quantity. So for when you're plotting the filter response, you have two responses. You have a magnitude response, how the magnitude of the filter is changing when you're changing the frequency. So the low pass filter response that we just discussed, that's a magnitude response. The magnitude is high at low frequencies, magnitude is low at high frequencies, right? And then you have the phase response or angle response, how the phase of the filter is changing as you are changing the frequency. So to write down the magnitude response, or to plot the magnitude response, or to understand the magnitude response and phase response, we have to write down their expressions. So let me ask you this. Now, if I want to write down the magnitude response expression, and either one, JF or whatever, let's just start with H of, let's say H of JF. J omega is the same. Or we can start with J omega because we derived that first. So H of J omega. All right, from the equation H of J omega, how I'm going to write down the magnitude of that complex quantity which is given in rectangular form. You can, you don't have to. Oh, just the denominator. Anytime a complex number is given in a fractional form, how do you calculate the magnitude of that complex number if it's given in a fractional form in rectangular coordinates? And that's what I told you to review that complex number, because I discussed that in my lectures as well, the complex number lectures. No, the simple question. Simple question is, if a complex number is given in a fractional form in rectangular coordinate system, how do you calculate the magnitude of that complex number in the polar form? What will be the magnitude of that complex number in the polar form? What will be the answer of this? This is a complex number written in a fractional form and in rectangular coordinates. Your numerator is in rectangular coordinate, the denominator is in rectangular coordinate. How are you going to find the magnitude of that? No. Okay, thank you. So you have the answer. The magnitude of that is going to be simply magnitude of the numerator divided by magnitude of the denominator. How do you calculate magnitude of the numerator? Square root of a square plus b square, and same goes for the denominator. Guys, I'm not going to say anything. This you are going to suffer if you're not going to understand the basics of complex number. You're going to suffer in every class. I will guarantee this. So better to learn it instead of suffering in every class. So magnitude of the numerator is 1 because it's 1 over 1 plus j omega over omega c. So magnitude of numerator is 1 simply, and magnitude of denominator is the square root of 1 plus omega over omega c square. That is the magnitude response expression for the low pass filter. Okay, now if you look at this magnitude response equation and if you plot that, magnitude of h of j. Our frequency is going from 0 all the way up to very high frequency. This is omega. All right, now plug omega is equal to 0 in this expression. What you're going to get? You're going to get 1. Omega over omega c will be 0, and you're going to be left with 1 over 1. So your first value, as we discussed earlier, is going to be 1. Okay, when omega becomes equal to cutoff frequency at omega c, what you're going to get? Plug omega is equal to omega c. 1 divided by square root of 2, which is 0.707, right? And that's why mathematically we proved that at omega is equal to omega c, the magnitude response of the filter drops down to 70.7% of its peak value. Peak value is 1, which is the numerator, as you can see. So at omega is equal to omega c, your magnitude is 0.707. And as omega becomes very large, omega over omega c is going to become extremely large. That means denominator is going to become extremely large. Let's say omega hits infinity, denominator hits towards infinity. That means the magnitude is going to drop down to 0, 1 over infinity. So now we have the filter response that I drew earlier, but now we have the filter response from the mathematical expression. Something like that. This is the magnitude response of the low pass filter. Generally, when we are plotting the magnitude response in MATLAB, or even when you're simulating it in PSpice, we keep the x-axis in logarithmic scale. Instead of the regular scale, we keep it in logarithmic scale. In MATLAB, the function is, instead of using plot function, we use semi-log x to plot the filter response, because semi-log x basically divide the x-axis into logarithmic scale. Logarithmic scale means what? That every time you multiply the frequency by 10. So going from 0.1 to 1, 1 to 10, 10 to 100 hertz, 100 to 1000 hertz. Every time you increase the frequency tenfold, on the x-axis, the distance between each tenfold of frequency is going to be the same. If you don't do that, and if you're plotting the response of the, and I'm going to plot it and show you. If you're plotting the response of a low pass filter, you have the values of capacitor, you have the value of resistor, and you found the magnitude response, and you're plotting it. Let's say your cutoff frequency is 1000 hertz, 1200 hertz, and you're plotting it up to 20,000 hertz, right? That means everything is pretty much happening in the earlier part of the frequency range, and nothing is happening in the later part of the frequency range. So what's going to happen? If you don't divide the x-axis into equal distance, it's just going to push all that frequency where everything is happening towards 0, because the range is just too large as compared to the initial part where your response is non-zero. And you will just see that it spike up and then goes down, and you will not be able to see a clear response of the filter. And I'm going to show you in MATLAB so you know what I'm talking about. So in general, filter responses are plotted as well as when you're doing the simulation. And then simulation in PSpice is done using what? Remember anyone? We did that in software class. What type of simulation we use when you're doing frequency simulation in PSpice? Yeah, all of you took PSpice with me. We did that. AC sweep. AC sweep. So anytime you are performing the frequency or noise, when you go to PSpice, it says noise or frequency. You perform AC sweep analysis, remember that. And in AC sweep analysis, when you look at that, it's going to give you two options. It's going to give you linear or logarithmic. So most of the time, we choose logarithmic. That will change the x-axis into logarithmic scale, and you can see the filter response very clearly, like this type of response. Okay, and again, we're gonna plot it in MATLAB, and then you're gonna plot it in PSpice as well, or simulate it in PSpice. So this is the magnitude response. As far as the phase response is concerned, now who is going to tell me again? Who is going to tell me if I want to write down the phase response of h of j omega, what will be the expression of the phase response from this expression, 1 over 1 plus j omega over omega c. Again, it will go back to ultimate question that if you have a complex number written in fractional form, how do you calculate the phase response of that complex number or phase of that complex number? Say it again. The phase of the numerator minus phase of the denominator. Excellent. Only one person knows about it. Phase of the numerator minus phase of the denominator. Okay. What is the phase of the numerator? No. That's the magnitude. It's a number. That's not phase. What is the phase of the? Where is this point located on the complex plane? On the real axis. What is the phase of the real axis? 0. It's 1 angle 0, right? 1 means what? 1 angle 0 degrees. So the phase of the numerator is 0 degrees. So phase of the numerator 0 degrees minus phase of the denominator. How do you calculate phase of the denominator? Hold on. Let someone else answer this. How are you going to calculate phase of the denominator? Huh? Okay. No, there's no denominator numerator. It's a plus j by jb or x plus jy. Yeah. B over a. Very good. So tan inverse of the imaginary part over the real part. So imaginary part is omega over omega c. Real part is 1. So it's simply tangent inverse of omega over omega c. Arctan of omega over omega c. Or simply negative arctan of omega over c. That is the phase response. All right, if I'm plotting the phase response, h of j omega. All right, tangent inverse omega over omega c negative sign, right? That means all the values are going to be negative, as you can see when we change the value of omega. That's why I put down the negative axis here. So at omega is equal to 0, arctangent of 0 is going to be 0. Tangent inverse of 0 is 0. When omega is omega c, tangent inverse of 1. What is tangent inverse of 1? I don't have to use calculator for that. Come on. When sine and cosine values are equal, what angle? (45 degrees). At 45 degrees, sine and cosine is equal. So when you take tangent of that, sine over cosine, you're going to get 1. Tangent of 45 is 1. So that's 45 degrees when omega is equal to omega c. Again, these are small things, but they are important thing to reflect that you are an engineering technology student. You don't have to pick up calculator or go to computer for smallest of the things. These are the things that you should know. At omega c, tangent inverse omega c over omega c, that is tangent inverse of 1 is 45 degrees, and we have a negative sign here. So that's negative 45. And when omega becomes very large, arctan of a very large number, tangent inverse of a very large number, what will be the result? What angle are, at what angle tangent becomes an extremely large value? 90 degrees, yep. Because remember, sine of 90 is 1, cosine of 90 is 0, right? So 1 over 0, or you cannot do 1 over 0, but as you're going close to 90 degrees, you're taking the limit, then sine is increasing in value, cosine is decreasing in value. So tangent, which is the ratio between sine and cosine, is blowing up. So at 90 degrees, it's basically extremely large. So it is going to hit negative 90 because of the negative side outside when omega is going to become very large. So your phase response is going to look like something like this. It's very hard to draw on this pen tablet. Easy to write, but hard to draw. So something like that is going to be the phase response. It's going to be asymptotic along negative 90 degrees as omega is going to keep on increasing. So this is the first order passive RC low pass filter. And these are the response curves. If I give you an example, design a first order passive RC low pass filter with the cutoff frequency of 5 kilohertz and C is equal to 100 nanofarad. Design a first order low pass filter RC. Cutoff frequency that you're designing for is 5 kilohertz, and capacitor value, you go to your kit and you say, oh, I have 100 nanofarad capacitor. Let's see what value of R I can find for my low pass filter with the cutoff frequency of 5 kilohertz if I'm using 100 nanofarad. Now, some values might not be very wise to use in a design. And what are those values? Very low values of resistor or very high values of resistor, right? Those are not very good values to use because they very low values are susceptible to noise, the low level noise, which is I forgot, it's called pink noise or something. And likewise, the very high values are also susceptible to noise. Generally, in between, like in kilo ohms or high 100 ohms, those values are good to use for resistors. They are more stable. And tolerance are also better for those values. But anyways, let's see for 100 nanofarad, what value of R we're going to get. If it is too small or extremely large, then we can choose another value of capacitor such that we can find a good, nice value of resistor. Cutoff frequency is still going to be 5 kilohertz. Because remember, your cutoff frequency, omega C, is 1 over RC. So you can either change the value of capacitor or change the value of resistor to get the same cutoff frequency. All right, so we know FC, we know C, we need to find R. The first thing we're gonna do is we know that omega C is 2 pi FC is equal to 1 over RC. So the resistor value is 1 over 2 pi fc times c. All right. What is the value? 318 ohms. Not a very good value. So let's go ahead. 318 ohms. So R is relatively small. Let's choose C is equal to, instead of 100 nanofarad, we choose 10 nanofarad. So the resistor is going to increase by 10-fold. So it's going to become 3.18 kilo ohms. So we reduce the value of resistor by 10 and the value of capacitor by 10, and the value of resistor is going to increase by 10 because their product, of course, is going to be the same. And this is a nice value, 3.18 kilo ohm. And now we're going to plot it. Plot the magnitude response and phase response. So let's go ahead. Let me open Octave, and then I'll. So when you are doing plotting, what is the first thing that you define when you're plotting a response? Yeah, you define component value, and then what? What initial? You said initial what? We're plotting against omega, right? We're plotting against omega, or we can plot against f, whatever. So what we are going to define, the vector for the x-axis, the vector for f, or vector for omega, of course, because you're plotting against that vector. That means you have to first evaluate all the values of the magnitude response and the phase response versus f or versus omega, based upon which x-axis you are taking, f or omega. Okay, so let's go ahead. Let me do it here. So let's go ahead and define R is 3.18 exponent 3, C is 10 nanofarad. Those are two values of component. And then we're going to go ahead and define, let's plot against f. So f is equal to, now if you're plotting logarithmic response, then remember log of 0 does not exist. So if you take the first value to be 0 for the frequency, whether it's omega or f, it's going to generate a warning. It's not going to give error, it's going to plot it, but it's going to generate a warning. And same thing goes in PSpice, it's going to generate a warning because log of 0 does not exist for the x-axis, that is. So generally you can go from, let's say, 0.1, instead of starting at 0, 0.1, and then since our frequency is 5 kilohertz cutoff, we want to go at least, so 5 kilohertz, next is going to be 50 kilohertz, and then 500 kilohertz. So let's go to 500 kilohertz, and let's increase our interval to with the 100 ohms, 100 hertz, and go to 500 kilohertz. Again, there is no rule for this, remember. If you're going to choose interval very small, it's going to take longer to evaluate and print because you're plotting too many values. If you're going to choose that to be very large, you're going to plot only few points and your curve is not going to be very nice. So you just have to think of a good value, use it. If it doesn't work, then go back and change the interval or whatever. All right, now the magnitude response. Magnitude, what happened to 5? So magnitude response, I have, or actually first let's go ahead and evaluate H. And then because magnitude and phase responses are coming from the equation for H, and our equation for H is what? 1 over 1 plus, and since we are doing F, so 1 over 1 plus J, F over FC. In this case, FC, actually let's define FC first. So omega C is equal to 1 divided by R times C, and FC is omega C divided by 2 times pi. So we define the value of cutoff frequency, FC, which is omega C over 2 pi. And now we're going to calculate the point from the transfer function. H is equal to 1 divided by 1 plus I times F over FC. Now you do have to put a period before the division because F is a vector and it's in the denominator. F over FC, you don't have to put a period because FC is not a vector. FC is just a scalar value. So this is going to calculate all the points for the transfer function in complex form from 0.1 F value all the way up to 500 kilo F value. And you don't have to display those, that's why I put a semicolon. And now how we are going to calculate the magnitude response from this? Anyone remember that? What is the MATLAB function to calculate the magnitude response? Absolute value, exactly. ABS, absolute. We did that in chapter 10, chapter 11. Or you can also use what? This is the rectangular form. You can also use pole, the function that we have, pole rec. So if I use mag of H and phase of H is equal to, now in my rec pole function, I'll try. I don't know if I wrote that function for matrices and vectors or only for scalar values, but let me try first. Rec pole H. Okay, it seems like it worked. And now I have the magnitude of H and I have the phase of H. Now, if you don't have the function, of course, what you're going to use? Absolute to calculate the magnitude instead of a square root of x squared plus y squared. That you can also use. You can also use a square root of real of H square plus image of H square. That's going to give you the magnitude. And then, of course, for phase, you're going to use angle function. Angle of H times 180 by pi is going to give you the response in degrees. I have the rec pole function, and I'm assuming my function also works for vectors, not just scalars, because it didn't give me any error. But if the values are correct or not, we're going to plot them, and then we're going to look at them. So let's go ahead and plot first the magnitude response. So let's call figure 1. And I'm going to plot, instead of using plot function, actually I'm going to do both. I'm going to do plot and I'm going to do semi-log x. So let's go ahead and do both in a subplot. So subplot subplot 2, 1, 1. I'm going to divide my figure into 2 subplots, and the first one I'm going to plot using linear plot. Plot f comma magnitude of H. My line width, I'm going to keep a little thicker, 2. X label is going to be f in hertz, and y label is going to be available. I'm just going to write down magnitude response of H, J, and backslash omega. And my title is going to be, if you have any question, guys? Title, linear magnitude response. Okay. So that's my subplot 1. And my subplot, subplot 2, 2, comma 1, comma 2. Just 1 second. Let's see who was. Give me this 1 second. So subplot 2 is going to be the logarithmic plot, semi-log x, where x-axis is going to be, instead of linear, I'm going to do logarithmic. So f, comma, magnitude of h, comma, same thing, line width. I'm going to keep line width 2. And I'm going to plot the logarithmic response in a different color. So let's say I plot that in magenta color. So comma m is going to give me magenta color. The first one is going to be in the blue color, the default. And I'm going to keep the rest of the stuff to be Control C, Control V, and Control C, Control V, and this is going to be logarithmic. Okay. So observe how the response look like, and that's what the difference I was telling you about. The first one is linear. Doesn't look like very nice low pass filter response because our frequencies are just so small. 5 kilohertz is just so small that I plotted the response up to 500 kilohertz. Everything is happening in a small range of frequencies, and it is pushed towards 0. Whereas the second one is x-axis is in logarithmic scale. So each tenfold of frequency is equidistant. So it's going to give you a very nice view up to 5 kilohertz, somewhere over here. And then from 5 kilohertz to 50 kilohertz and 50 kilohertz to 500 kilohertz, all will have the same interval. So irrespective if your response is in the lower spectrum, it is going to give you a very nice, clean looking response. I'm going to show you the code if you are here. If you're working on the code, this is the code. I'm sorry? You have what? Which line you're talking about? That's my function. That's my function. If you don't have the function, then just use absolute and angle. Yeah. Right. Yeah. Just use ABS of H for magnitude and angle of H for the phase. Yeah, use ABS of H and assign it to magnitude, and angle parentheses H, assign it to phase. The angle, remember, is in radians, so multiply that by 180 divided by pi to convert that into degrees. Okay. Now, again, we're not going to spend a lot of time at this time during the class. This is there, spaced it in the notes. Notes will be available. So make sure you do that so you can get some practice to plot it. But the reason I was doing this is just to show you again the difference between the linear response and when the x-axis is logarithmic response of that. So this is why we prefer plotting the frequency response on the logarithmic scale, because it gives us a very nice view of the response of the curve. The first one, although it's a correct response, but it doesn't show the low pass filter response as we want to see it. All right, in the simulation or in MATLAB plot, how are you going to figure out if the plot is given to you or a simulation is there? How are you going to figure out what is the cutoff frequency? You are going to move your cursor on the plot until you hit 0.707 and then read the corresponding x value, and that's going to be your cutoff frequency. So if I move my cursor here, and you can see that value changing in the bottom, and in MATLAB it's easy because the move cursor moves along the curve. This one is free moving cursor, but you have to go and then see when y becomes 0.7071 somewhere right here, 705, and I can see 51 something. It's hidden by this hand symbol. What is that? Annotate. Okay. So anyway, so that's how you're going to figure out that in the simulation, move your cursor to 0.7071, or on the plot, move your cursor to 0.7071 from the plot, that is. And of course, from the equation, you can always figure out what is the cutoff frequency. You equate the magnitude. If you don't know what is the cutoff frequency, you equate the magnitude response, which is the equation of the magnitude response. You equate it with 0.7071, put the 0.7071 here, and solve for the cutoff frequency. And you can find what value of omega is going to result in the cutoff frequency. In this case, we already know that it's going to be 1 over RC. But in general, if the equation, you don't know from the equation what is the cutoff frequency, if it's a different equation, then the way you do that is equate the magnitude with 0.7071 and then find the corresponding value of omega. That value of omega is the cutoff frequency. Yeah, go ahead. So in Octave, I didn't see that. As I said, if you're doing in MATLAB, then your cursor moves along the curve. So it's much easier. If you're plotting in MATLAB, it's going to move along the curve. It's not going to move freely. In Octave, I did not find that function that it moves along the curve. So, it's always, you have to be very careful as it's free moving cursor in Octave. So, again, Octave is free, remember. So there are some issues, but it's free. So cannot really complain. Okay, what about the phase plot? Similar, we can do the phase plot like we did the magnitude plot. So for phase plot, our equation of the phase plot is H is equal to, we already have that actually, phase of H, we already had that. So we're going to go ahead and plot that. I'm going to copy these, Control C, and oh, what happened here? It went ahead and plotted both things. Oh, it didn't plot the other one. Okay, let's go ahead and what is that? Control C. Let's do figure. Well, I deleted that figure, so it doesn't really matter. So I'm just gonna go with this, and this is gonna change to angle or phase of H. So phase response, and then one. Where is it? That's why I don't like Octave. One, go up. It's not gonna go up. Okay. Oh, I hate Octave. All right, I'll have to write that again. So subplot this. Let me copy just this line. I don't want to rewrite it. And then let me go and then do angle, F in hertz, and then plot phase of H, right? That's where we put the magnitude. Yeah, phase of H. And then I'll just put title here, comma, title. Response linear. Okay. Phase response linear. Response. And let's go to now second one. Let's go ahead and copy this. Control C and Control V. Oh. Okay. One. Subplot logarithmic log, and instead of plotting, I'm going to use X. Semi-log X, semi-log X. All right. Oh, 2.1.2. Okay. Let's go and do semi-log. Okay, this. And then, is that my phone? or someone else's phone. It's my phone. 2-1-2. So that's our phase plot right here. Going from 0 degrees to 90 degrees. One other thing that is usually good is if we kind of tighten up the axis, so it removes the white spaces. So let me show you that as well. Let's do first linear, and at the end I'm gonna do axis tight. You can define your axis. All what I'm going to do, I'm going to tighten it up a little bit. So it's going to remove the white spaces, y-axis and x-axis. Axis tight. And I'm going to do the same for the other plot. And I'm going to do axis tight. I'm going to change the color of that as well to magenta or some other color. Cayenne, let's say. So this is my phase plot. Now I tighten up the axis, so you can see it's going up to negative 90 degrees, negative 80 and negative 90. So magnitude response and phase response are these two responses. Okay, any question guys so far about the first order RC filters? Things are clear? Things are clear? You guys understand how you're going to recognize the filter as far as low pass, high pass? Yes. Yeah, so if a transfer function is given to you, right? If your transfer function is given to you for any order of filter, right? Not just the first order, but any order of filter. And someone asks you, this is the low pass filter, and give me, figure out the cutoff frequency. Then you know that for the low pass filter, the transfer function, no matter what order it is, your transfer function at the cutoff frequency, the transfer function value is going to be equal to 0.707, magnitude of the transfer function. So you equate that magnitude 0.707 and find the corresponding value of omega from the transfer function, and that omega will be equal to omega c. I don't know if is that what you're asking or what exactly? You can do it graphically always, remember, right? Always graphically. But if you don't have the graph in front of you and you have to do mathematically, no, hold on. You don't, you are taking the magnitude of the transfer function and you are evaluating that magnitude when the value of that magnitude is 0.707, and you're trying to find out what is the value of omega at which the magnitude is going to become 0.707, right? Transfer function can be written any which way, but it will be written in terms of omega. So let's say 2.05 exponent 5 omega over 1 plus j5 omega something, right? This is the transfer function given to you. And I say, okay, I tell you, hey, this is the transfer function of a high pass filter. Figure out what is the cutoff frequency. So what you're going to do? You're going to take the magnitude of the transfer function, and then you're going to equate that magnitude with 0.7071 and figure out what is the value of omega from that transfer function. And that value of omega is going to be omega c. Yeah. Yes. Are we going to go over it? Yeah. No, we're going to go. I'm just giving an example. Yeah. All right, guys. So let's go ahead and take a break, short break. I'm just going to be here. And then we're going to go and start high pass filter, RC. And from there, we're going to move on to other things. Now, high pass filter is the opposite of low pass filter. That is, it stops the output at low frequencies and let the output go at high frequencies. And all you have to do is to switch the position of R and C. So capacitor is going to be in series and resistor will be in parallel with the output. And again, apply that same logic as how you're going to recognize if it's a high pass or low pass filter from the change in reactance, So again, start from 0 frequency, go up to high frequency, and see how the output is going to be changing. That is, in response to the change in the reactance of the capacitor, how the output is going to be changing. So think about it. Start with 0. Reactance of the capacitor is going to be at frequency 0. Reactance of the capacitor is? Yes. Reactance of the capacitor when frequency is 0. Come on, Rodley, you don't have to go back and check. Yes, Mike? Is what? Yeah, it's very high, it's almost infinity, right? So it's going to be open circuit. That means no current is going to pass through it. Output will be 0. All the voltage is going to appear across the capacitor. All the input voltage is going to appear across the capacitor. No voltage is going to be across the resistor. So at omega is equal to 0 or F is equal to 0, output will be 0. As you start increasing the frequency, reactance of the capacitor starts going down. Eventually, at very high frequency, reactance or capacitor start acting as a short circuit because reactance become such a small value, and pretty much all the input voltage is going to appear across the output voltage, and none of the voltage is going to be dropped in the reactance of the capacitor when it's going to become almost 0 at very high frequencies. So at high frequencies, output is equal to input. At low frequency, output is 0. It is acting as a high pass filter. Let's write down the output first and then transfer function. So the output equation, who's going to tell me the output is going to be equal to? Oh, the equation for output. Yes, it's not in your notes. Hold on. Yes, Rudley. Output in terms of input and RC or RXC. All right, Gloriana, what will be the output expression in terms of RXC and input? Come on. All right, Mike. Say it again. Okay. Voltage division as we did in the last time. Right? R over R plus XC times Vn. So the transfer function. Oh, by the way, if you are calculating the magnitude, of course, of the output, and you have the magnitude of H of j omega, remember H of j omega is the ratio between the output and the input, right? So let's say you're trying to figure out what is the magnitude of the output for a specific value of the input, and you have the magnitude of H j omega. So all you have to do is to multiply H j omega magnitude times input magnitude, and that's going to give you the output magnitude. Likewise, if you're trying to figure out what is the angle or phase of the output, and you have the phase, or you have H of j omega, magnitude and phase, and Y and V input, magnitude and phase, how are you going to find the output phase? You add them together because H and input are multiplied by each other. So this is going to be R over R plus XC, R over R plus 1 over j omega C. J omega RC over 1 plus j omega RC. All right, magnitude response. What will be the expression for the magnitude response? I was going to tell me that. Yes, magnitude response. No. Okay, and what is the magnitude of the top? You don't put J when you're calculating magnitude, first of all. Why you're putting a square root and then putting omega RC? It's omega RC angle 90 degrees, right? So omega RC is the magnitude, 90 degrees is the phase. So this is omega RC right here. Omega RC is the magnitude of the numerator. What is the magnitude of the denominator? One plus omega RC is. Okay. So that's the magnitude response. And once again, to see the value of omega that will be the cutoff frequency, we can easily see that from this at omega is equal, let's write this down here. We can write this down as divide the numerator and denominator both by R. Actually, we don't have to do that. We can just, or even if we do that, numerator and denominator by RC. So omega is going to be left in the numerator, and in the denominator we will have omega plus omega square plus 1 over RC square. We divide both numerator and denominator by RC. So when omega is equal to RC, and again you can do the calculation by 0.707 as I told you to find the value of omega. At what value it's going to become equal to 1 over square root of 2. But just by observation, when omega is 1 over RC, then it's going to be 1 over RC square plus 1 over RC square, so 2 over RC square, and omega is equal to 1 over RC. So that's going to give you, when we eliminate, of course, the square root, you're going to have a square root of 2 times 1 over RC in the denominator at omega is equal to 1, omega is equal to RC. And in the numerator, we'll have 1 over RC. So you're going to be left with 1 over square root of 2 at omega is equal to RC, or 1 over RC, sorry, not RC, 1 over RC. H of j omega is equal to, we can use this equation as well if you want, or this equation, whichever. We can just use this equation. 1 over RC times RC divided by the square root of 1 plus 1 over RC times RC squared. So we are using this equation, right? So RC cancelled out, RC cancelled out, and you're going to be left with 1 over the square root of. So for high pass filter also, the cutoff frequency is omega is equal to 1 over RC. All right. As far as magnitude response go, what will be the magnitude response expression? Who's going to tell me now? The phase response, sorry, not magnitude. All right, guys, phase response equation from this. What is the numerator angle? What is the numerator angle? It's written over there. Huh? 90 degrees numerator angle, J. You guys are not very good engineers or mathematicians. I'm telling you guys. A good engineer or a technology person observe and respond back. For easy things, of course. For hard thing, you go and do research, you do math, whatever. But for easy things, you observe and you respond back. All right, what is going to be the magnitude or the phase for the denominator? Inverse tangent of omega RC. So that's the expression for the phase response. 90 degrees minus arctan of omega RC. So for the magnitude response, of course, it will be the high pass. How do you know it's going to be high pass? We look at the magnitude response expression, this one or this one, whichever. When omega is going to be small, the numerator is 0. H of j omega is 0. As omega is increasing, when omega is going to get to, of course, 1 over RC, we know that the magnitude is going to be 1 over square root of 2, cutoff frequency. And when omega is going to become very large, the numerator is going to be large, as well as the denominator is going to be large. So when you have, let's say omega goes to infinity, that means the numerator is going to be infinity, as well as the denominator is going to be infinity. And when you have infinity over infinity, how do you find out the value? You apply. Anybody remember that math when you were learning limits? What was that? If you have 0 over 0 or infinity over infinity, what you used to apply to get the response? All right, everyone forget about it. Anybody remember L'Hopital rules? They write it L hospital, right? L hospital, but call it L'Hopital rule, L'Hopital, whatever they call it. So if you have infinity over infinity, you apply the limit. Omega tends to infinity, take the differential of the numerator, take the differential of the denominator, and then apply omega tends to infinity again. And again, if you're getting 0 over 0 or infinity, then you take the differential again and then apply it again. But anyways, once you do that, you're gonna get that when omega tends to infinity, then h of j omega is going to be equal to 1. I'm not doing all the derivation, but it's gonna come out to be 1. As far as phase is concerned, when omega is 0, what is gonna be the phase? 90 degrees. And when omega reaches very high value, or when omega is 1 over RC, the phase is going to be 45 degrees, because this is going to be 45, 90 minus 45 is 45. And when omega reaches very high value, what will be the phase? 0 degrees, because this is 90, 90 minus. So this will be positive phase from 0 to 90 degrees at the cutoff frequency is going to be, it is going to be 90 degrees. So I'm not plotting right now in MATLAB because I showed you how to do it and you can do it. I'm just going to plot it here, omega and the magnitude response. And the magnitude response is going to be something like this. At omega is equal to omega c, your magnitude is going to be 1 over square root of 2 for the transfer function. And as is going to hit infinity, the magnitude is going to be 1. So that's the magnitude response of this high pass filter. And then the phase response. Phase response of h of j omega. It's going to go from 0 to 90 degrees, passing through 45 degrees as omega c. And eventually, 90 to 0 degrees, doing opposite. 90 to 0 degrees. 90. And omega c is going to be 45 degrees. Something like that. Really, I don't like this. Let me go ahead and do it again. Something like this. That might be a little better. 90, 45 at omega c, and 0 as omega tends to in. So this is the phase response and the magnitude response of the filter. So these are low pass and high pass RC filters. Now let me ask you a question now. Think about now our L low pass and high pass filter and suggest if I want to do our L low pass filter. Input, output. Suggest how R and L will be connected. All right, so according to Chris, L on top and then R in parallel with the output. All right, Chris, explain why did you say that? Okay. You have to again think about the reactance, not just say, oh, inductor is opposite of capacitor, so I'm going to switch it. No, you have to scientifically, in engineering terms, again, as I said, you have to think about how the reactance is changing because that is going to change the frequency response. In this case, XL is j omega L. And at low frequencies, j omega L is going to be what? At low frequencies, it's going to be high. Omega 0. How is it going to be high at omega is equal to 0? It's going to be low. It's going to be short. Remember, inductor is short at DC once it's fully charged, right? J omega L is 0 at DC. So at low frequencies, it acts as a short circuit. The output will be equal to input. At high frequencies, XL will open. XL is going to be very high. Start acting as an open circuit at omega is equal to infinity. Output is going to become 0. So this is going to become a low pass filter, letting the input go through the circuit at low frequencies and stopping the input at high frequencies. So that's going to give you a low pass filter. Now what I want you to do is, I'm not going to solve it in the class, but I want you to do the derivation of the input drive h of j omega, determine cutoff frequency expression, and let's say design for FC is equal to 7 kilohertz. Choose good values of R and L, and plot the magnitude and the phase responses. All right, I want you to do this thing, because again, we did for RC, similar thing you have to do for RL, right? So there's no point of me spending that much time doing the same thing for RL. So do these 4 things as you saw, and do it. Don't just leave it, because if you don't do it, and if I do give this problem in, let's say, exam or quiz, and if you have not done that, you will not have any practice, and you're going to end up getting a 0. So make sure you do it. So that's your RL low pass filter. Now, for RL high pass filter, of course, notes will be posted, so that is going to be, you can always check it. RL, first order RL passive high pass filter. All right, now it's going to tell me where the components will be connected. Very good. Opposite of the low pass. So first come resistor in series, and then come inductor, not capacitor, inductor in parallel. So XL is going to be very small at low frequencies. That means it's going to be short circuit, output will be 0, and XL is going to be very high at high frequencies, start acting as an open circuit. So input and output are going to become equal at high frequencies. Now do the same thing for this as you're doing for this, these 4 questions. Drive the transfer function, drive the expression for the cutoff frequency, design for the cutoff frequency equals 7 kilohertz, choose good values of R and L, and plot the magnitude and phase responses. Now we are going to move on with the band pass filter, which we also called resonant circuits. And these are second order. So second order series RLC bandpass filters or RLC resonant circuits. So it has two names basically. You can call it a bandpass filter or a resonant circuit, and it's going to be a series one. We are looking comes in both, of course, series RLC or parallel RLC. We're going to start with the series, and that's where you have your last lab basically that I think I have written is from this topic, if I remember correctly, and it's been 4 or 5 years, so I have to go back and check. Okay, 1 second, open my old notes. All right, so bandpass filter basically let a band of frequencies pass through it and stop the low frequencies and high frequencies. So if this is your omega or F, and this is the magnitude response of a bandpass filter, Hj omega or Hjf, then the response curve looks something like this. Something like this. Different variables that you have here. The frequency at which it reaches its peak value, that's called the center frequency and represented by omega naught or F naught. So omega naught or F naught is equal to resonant or center frequency. And we're gonna see what frequency expression is gonna be there for resonant or center frequency. Now you have two cutoff frequencies for bandpass filter. Why two cutoff frequencies? Because your 0.70, by the way, at the resonant frequency, the magnitude is going to be 1 of the transfer function. So that's the peak value, right? Where the magnitude is 1. Now you have two values at which your magnitude is going to be 1 over square root of 2. So this is your 1 over square root of 2. You have a frequency on the lower spectrum, which we call lower cutoff frequency, and you have a frequency at the upper spectrum that you call upper cutoff frequency. So this is generally represented by either in terms of omega. This is omega 1 or omega lower L, and this is omega 2 upper cutoff frequency or omega U. Lower cutoff frequency on the lower spectrum and upper cutoff frequency at the upper spectrum. And the difference between the lower and they can be, of course, so omega 1, omega low, or F1 and F low. This is lower cutoff frequency. And omega 2 or omega upper or F1 or F upper. This is upper cutoff frequency. The difference between the lower cutoff and upper cutoff is represented by the bandwidth of the filter. Bandwidth of the filter. Generally represented by B. I'm just showing BW, but B is equal to BW, which is equal to omega upper minus omega lower is the bandwidth, or F upper minus F lower. So these are important quantities. Now, in general, we also have the stop frequencies as well for every filter. We are just discussing the cutoff frequency in the pass band. Also, by the way, the band of frequencies where all the frequencies are passed is called the pass band. Then you have a transition band, and then you have a stop band. There are 3 bands in every filter. So for example, the high pass filter, you have the cutoff frequency here. Then you also have in general the stop frequency, and then the cutoff frequency, and basically your anything after the cutoff frequency is the pass band. So basically you have the stop band in general from 0 to the stop frequency. Stop band. So everything there will be stopped for practical filter, that is. And then from the stop band to the cutoff frequency is what we call transient band. And we want the transient band to be as narrow as possible. We don't want it to be wide, because frequencies can still be passed through the transient band because the magnitude is not 0 of the transfer function. So when you multiply the magnitude of the transfer function by the input, you can get some value for the output. Yeah. I'm sorry? Operating frequency, generally we want it to be in the pass band. We don't want the operating frequencies to be either in the transient band or a stop band. We want them to be in the pass band, so that you get the maximum amplitude at the output over all those frequencies where the filter is operating. It's letting the input pass through. So for every filter, we have 3 bands, 3 frequency bands. You have a stop band where the frequencies are stopped. We have the transient band, which is between the stop frequency and the pass frequencies. And then you have the pass frequencies or pass band where the frequencies are let go through the circuit. Similarly, for the low pass filter, we have 3 bands. And for the band pass filter, we also have the same 3 bands. You have of course, you have the pass band, which is over the bandwidth. So this is your pass band over the bandwidth, pass band. And then you have on the lower side, you have a stop frequency somewhere over here, let's say. And on the upper side, you have the stop frequency, omega, let's say lower stop, and omega upper stop. So that's going to be a stop band on the lower side. And that's going to be a stop band on the upper side. And between that, that's going to be transient band on the lower side, and that's going to be the transient band on the upper side. But for the sake of simplicity in this course, we are only considering your pass band, which is the bandwidth. We're considering the center frequency and the cutoff frequencies. But we are not considering right now the stop band or stop frequencies. But when you're designing filters, then you do consider the stop frequencies as well. Like when you design filters in DSP and integrated circuits, then we will have to consider the stop frequencies as well. Okay, as far as circuit is concerned, the second order means it has 2 reactive components, L and C, and they're connected in series. So the second order filter series RLC circuit. All three components are connected in series. And the resistor is assumed to be your load. This is your V in J omega, your L, X of L, your C, X of C, and your R, which is acting as a load. So the output is taken across the load. Yeah.
First order.
Mhm.
You notice that components, depending on their orientation, say fairly lower.
Yes.
But does the orientation of the capacitor?
It doesn't matter. It doesn't matter. This still be considered as a pass band filter, a bandpass filter. Okay, so let's go ahead and derive the expression for the transfer function. So let's first do V out of J omega. All right. So it's going to tell me what will be the expression for V out of J omega for this circuit. Yes, rudely. V in. Yes, very good. Voltage division will give us V out is equal to V in J omega times R over R plus XL plus XC. R over R plus J omega L plus 1 over J omega C. Therefore, H of J omega is V out J omega over V in J omega. No, not showing the magnitude right now. Let's show the expression is equal to R over R plus J omega L plus 1 over J omega C. So that's the transfer function of this. And if we simplify it and write it down in terms of denominator over numerator, then we are going to get J omega RC divided by J omega RC plus J square, which will be -1. So negative omega square LC plus 1. In terms of real and imaginary component, I'm going to write it down. Numerator J omega RC, and then real part first, which will be 1 minus omega square LC, and then the imaginary part plus J omega RC. Okay, so the magnitude response, who's going to tell me what will be the expression for the magnitude response? Omega RC very good, excellent. So that's going to be the magnitude expression. Omega RC is the magnitude of the denominator and numerator, and square root of a square plus b square, magnitude of the denominator. As far as phase, so that's the magnitude response. All right, phase response. All right, who's going to tell me what will be the phase response expression? Okay, 90 minus 90 is the phase of the numerator. That's the phase response. Right. So we're going to continue this, but before we leave, we have about 5 minutes. I want to draw the response curves for an example. So let R is equal to 10 kilo ohm and 10 kilo ohm. L is equal to 50 millihenry and C is equal to 1 nanofarad. Draw or plot rather. Nobody's going to draw here. Plot the magnitude and the phase response of the filter. All right, so we have the transfer function, we have the value of R, we have the value of C, and we have the value of L. We are going to go ahead and plot the response of the transfer function, both magnitude and phase. R is 10K, L is 50 millihenry, and C is 1 nanofarad. Let's go ahead and define omega, range of omega. Omega is equal to, again, I'm going to go from 0.1 to, or I can just define the f value since we are giving f. No, we are not giving f. We're going to calculate f from the response curve. So let's go ahead and do f is equal to, we go from 0.1. Again, let's go to 100 step size, and let's go to 2 megahertz, so 2 exponent 6. And then to omega is equal to 2 times pi times f, because our expression is written in terms of omega. And let's go ahead and write down the expression first. So my H is omega RC, omega times R times C times I, j omega RC divided by 1 minus omega square LC, 1 minus omega square times L times C as the real part, and then the imaginary part is I times omega times R times C. That's my denominator. And then I'm going to go ahead and calculate the magnitude and phase. I'm just going to use my function, magnitude of H and phase of H is equal to rec pole H. And again, if you don't have the function, you can just use absolute value to calculate magnitude, absolute function to calculate magnitude, and angle function to calculate phase. In MATLAB, of course. And then I'm going to go ahead and plot the magnitude response and phase response in two different figures. So figure 1, I'm going to use semi-log x, semi-log x. I have f comma magnitude of H, and I'm going to increase the line. So line width to be 2. X label in hertz, and Y label is the magnitude of H of j omega. And title is magnitude response. Okay. Oh, put period instead of comma. And let me also activate grid and tighten up the axis. Should plot for a little more length. So, but anyways, actually, let's do that. We are going from up to 2 exponent 6. Let's go ahead and do maybe 10 exponent 6. Magnitude. Log x. Clear. Do it again. Okay, f is this. Oh, omega. Okay, omega I did not change. That's why. Because omega is defined over f. Omega is this. And then r is this. Is magnitude. And then semi-log. So this is my plot for the magnitude response. The center frequency is approximately from the plot is about 22K, 22.3K, close to that. Of course, it's not accurate. 23K, something like that. Cutoff frequencies we can check from the plot, 0.7071, 0.70707, about 11.3K on the lower side, and 44K on the upper side. So 44 minus 11, 33K. Bandwidth is about 33 kilohertz. And again, we're going to derive those equations so we can calculate them mathematically as well. But this is your plot. Anyone else getting the same result? Same plot, guys? Magnetic response? And the phase plot is going to be the same like we did for low pass filter. So this is the phase response. Phase response or phase response. -2, and this is phase of H, and I'll plot it with different color. Let's plot it with green color this time. And the phase response is this, starting at 0 and going, starting at 90 degrees, I'm assuming this is 90 degrees and going to -90 degrees. So between 90 degrees and -90 degrees. Let me change this to okay, and that's where we are going to stop today. That's 11:30. If you have any question, I'm here for a few more minutes. You can ask me any question that you may have. We're going to continue from this point on Monday. And what we have to do, we have to calculate the mathematical expressions for the center frequency, the cutoff frequencies, and the lower and upper cutoff frequencies, that is. The bandwidth expression, there's a quality factor term that we use with the bandpass filter. We're going to look at the quality factor of the bandpass filter. And then we're going to solve, we're going to design a filter, bandpass filter. So that's what we're going to do next week. And then, next Monday. And then we're going to go from there. I don't know. I don't think I'd have enough time to start. Let's see, what is this? Yeah, I don't think I have enough time to start the Laplace transform technique. So we'll see. First, we're gonna finish this, and then we'll decide what to do next. Maybe I just keep going over the resonant circuits and all those things. Okay, guys. Yes. Yeah, magnitude response is right here. This is the magnitude response.